Hello everyone. In today's lecture we're planning to revisit the topic of power and basically look into calculation of power when the signals are sinusoidal. We have already covered the topic of analyzing circuits where the signals are sinusoidal. We using phasors and all the tricks that we learned. Now we're going to try to calculate powers and make more sense of the idea of calculating power in RLC circuits when the signal is sinusoidal. So the basic concept that we already know about is that for calculating power in an electrical system, you take the voltage that is applied across the component and multiply it by the current that is passing through it. And we have a certain convention. Basically, if the current is actually going into the positive terminal, you take this just value of the voltage and multiply by the current. And if the current goes into the negative terminal, you take the value of voltage and current and then multiply by a negative. And using that convention, if the power becomes a positive value, then this component is actually consuming that power or turning it into a different form of energy other than electrical. And then if it's negative, it's basically generating that power. Now, we have already covered all that. Let's just pay more attention to specific components that we have learned and extend our calculation to a case where the voltage and current are sinusoidal in nature. Okay, so with a simple resistor, if the voltage that we're applying here is sinusoidal, obviously the current is going to be sinusoidal. We already know that. But more than that, we know that the voltage and current in the case of a simple resistor are in phase. So if I basically, the reason is that the relationship between the voltage and current is a simple Ohm law, it's a simple linear equation where the current is basically voltage divided by the resistance, and because of that, you don't change any information about phase in the signal. So if I want to show you what happens in the time domain, let's assume that the voltage is a simple cosine of omega t. So with the cosine of omega t, the waveform is going to look like this. And it repeats, right? So this is one period of the signal, which is 1 over frequency. And by now we know that's 1 over basically frequency. 2 pi times frequency is omega. So if I want to write it in terms of omega, frequency has to be replaced with, so that's omega, let's write that down here. Omega is 2 pi f, so frequency is omega divided by 2 pi, and that would be 2 pi divided by omega. Okay, so that said, now we know, let's do this for a very simple case where the resistor is 1 ohm. So that simplifies everything. If that's the case, that I know that the current would be the voltage, which is cosine omega t, divided by the resistance 1. So the current is also a cosine omega t. So the two are going to exactly go on top of each other. Now, this color, if you can see that, that's the current IT, and the other current color was the voltage VT. Now, if you take these two and multiply by each other, multiply the two by each other, then you get the power at each point of time, right? So power, obviously, because the voltage is as a variable with time and the current is variable with time, then the power is also a function of time. So it changes. The power is something that has to be calculated for each moment in time, and it's changing. So the voltage ended up being cosine omega t. The current ended up being also cosine omega t. So this is cosine to the power of 2 omega t. So how does this look like if you want to show it here? Well, it's not that hard to see that down here the value is 0 all the way to this point where it becomes a maximum, basically, and then it goes down to 0 again. But now something interesting is going to happen. So this goes up, reaches a maximum. So it actually does this. Goes up, reaches a maximum, comes down, and then now when the voltage is negative, also the current is negative, and the two multiplied by each other actually becomes a positive number. You can see that this value, cosine to the power of 2 of omega t, is always a positive number. So this comes down, becomes 0, and then goes back up, and then comes back down, and then goes back up. So it's still changing in a sinusoidal way, but obviously different than the way that the voltage and current individually were behaving. You can actually turn this into 1 plus cosine of 2 omega t divided by 2. In other words, the frequency of the change here in this signal is twice as much as the frequency of the cosine and sine. And you can see that because one period of this signal is actually half a period of the signal voltage and current. So one period of this new signal starts from here, goes up, comes down, and that's one period. But this point was half a period of the voltage and current. You can see that. In other words, the frequency of this blue signal, which is now the power for this resistor, this is power, is twice as much as the frequency of the voltage and current individually. And in that sense, this component, first of all, always consuming power. But the power at some point becomes the power consumed at a certain amount of time becomes 0, and then it reaches a maximum, and then goes back to 0 and reaches a maximum. And if you want to know what the average of this function is, you can actually see that here. Because the cosine 2 omega t, average of a cosine over a period is actually 0, because half the time is going above the average and half the time is going below the average. And therefore, the average of P in this case is just 1/2. And you can see that there too. So this is the line. This maximum is actually 1, and this is 1/2. And so the average power that is consumed by the resistor, if you're only interested in knowing what the average power consumed by the resistor is just simply half. So this is an interesting situation where now we can extend that to arbitrary voltages and currents. So if generally speaking VT was, so if VT is an amplitude times cosine omega t, then the current IT becomes a certain amplitude, and this doesn't have to be the same. In this example that we did, for the simplicity, we assume that the resistor is 1 ohm, and in that case Vm and Im became the same, but that's not necessarily the case. And then if you multiply the two by each other, you get Vm Im divided by 2, which is the average power that is consumed here, plus Vm Im divided by 2 cosine 2 omega t. So this portion of the signal is the variable portion. This portion of the signal is the average. and to add it to each other gives you the instantaneous value of the power. So there's not much of complexity in the case of a resistor, and we can kind of understand how the current and voltage is the behavior, the alternating behavior current voltage impact the instantaneous value of the power and the average value of power that is consumed in the resistor. And at all times, the value of the power is positive, and that's expected because we know that resistors turn in electrical energy into heat, so they're consuming the power, and that's also represented mathematically and goes hand in hand with the kind of convention that we had to describe power. Okay, now in the case of an inductor, the situation is different in a sense that the voltage and current relationship is defined with a different equation, obviously. So we already know that the voltage across the inductor is equal to the inductance times the derivative of the current that is passing through the inductor with respect to time. So now, with that, let's now calculate the power, assuming that the signals are sinusoidal. So let's say IT is a cosine omega t in this case. So I'm taking it, so let's say it's IM, a maximum current times cosine omega t. So peak current times cosine, so alternating current. So now with that, Vt would be L Im d cosine omega t dt, which then it becomes L Im omega minus sine omega t, right? So I can rewrite the equation and turn it into its cosine form. So it would be L Im omega cosine of omega t plus 90 degrees. So up to this point, it's kind of understood that with this case of an inductor, the voltage ends up being 90 degrees ahead of the current. That's what you see here. Same frequency, obviously different amplitude, but then the relationship between the phase of the voltage and the phase of the current is such that the voltage is 90 degrees ahead of the current. So now if we look at the time domain plots of how the voltage, current, and the power would behave. So let's say we start with the current. So current changes like I cosine omega t, starts at t equal to 0, starts at the maximum, then it goes down, minimum, and then comes back up, and like that. So this is the current. Okay, so this is my IT. Now, the voltage is 90 degrees ahead. So the maximum has happened here at t equal to 0. This is a cosine of 90 degrees, which is 0. So it goes down, reaches the maximum here, and then comes back up, becomes 0 here, goes back up, maximum, and then goes to 0 again. So this is your pink. If you can see the color in the video, this is your voltage. So that's Vt. Now, when you multiply them by each other, you get the power. So the power, obviously, P, is equal to this multiplied by this. So L Im to the power of 2 omega cosine omega t times cosine omega t plus 90 degrees. So let's look at it here. So something interesting happening here. And notice between this 0 and that 0, the current is positive, the voltage is negative. So when you multiply them by each other, you get a negative value. but between the current being 0 and the voltage being 0 again in the next portion, now both voltage and currents are negative, so when you multiply them by each other it becomes positive, and then from this one to this one, now voltage is positive, the current is negative, so now the power again becomes negative, and then from this 0 to that 0 it just becomes positive again. So every time that the voltage or current crosses 0, first of all the power becomes 0, and then right after that it changes polarity. So if you want to draw it, this is going to look like this. It becomes, it's here, negative, and then 0, and then goes positive, then 0, and then goes negative, then 0, and goes positive, and 0 again. Right? So now this is our power. So a couple of things to notice. First of all, the average of this power obviously is 0. And also, as you can see, about half the time during obviously one period, exactly half the time the power is negative and half the time the power is positive. Now if you go back to the convention that we discussed earlier on about power, we mentioned that when we have a positive power, that means that the power is being consumed by that component or received by that component. And when the power is negative, that means that the power is generated by that component or delivered by that component. So in this case, it looks like that every time that the power is, per se, being consumed in the positive circle, right after that the power actually comes back in basically the next half period. So in reality, what is going on is that the inductor, as we could recall now from the physics of the inductor, is not really consuming the power, and rather receives the power and it conserves it in the form of kinetic energy, right? So that's what the inductor does. So during this half, all the power is where the power is negative, all this energy is being conserved, and then the next half, that energy that was conserved is going to be delivered back to the source, and then it just keeps repeating. So I can actually simplify this equation to this form. It becomes a minus L I m omega sine of 2 omega t. It's basically 2 cosine alpha times cosine beta. You can write it as 1/2 cosine alpha plus beta, and then cosine alpha minus beta, and when it becomes cosine alpha minus beta becomes cosine 90 degrees, that's 0, and then it becomes cosine 2 omega t plus 90 degrees, which is minus sine of 2 omega t, and that's what you see here. So let's check the polarity and everything. So at t equal to 0, the power is 0, and then first of all it changes with a frequency twice as much as the frequency of the cosine, the current on voltage, and that's obvious here. In both the green and the red have a frequency of omega, angular frequency of omega, where blue has twice as much of a frequency. It actually alternates twice as fast, so you can actually see that here, right there. And then it becomes negative and then positive, so it's a minus sign right there. Okay, so first of all, the average is 0 again. Then also we notice that the frequency is twice as much, and from this we can start concluding that the average power is really the only part of the power that is being consumed, in a sense that it transforms from an electrical domain to a different domain that is not going to come back to electrical domain. So in the case of an inductor, the average is 0, so there is no part of the power or the energy that actually transforms to a different a different domain. It actually all concerned in the domain of electrical, and then it just goes from one form to the other, kinetic to energy, kinetic to potential, and potential back to kinetic, and it just keeps repeating like that. So with that in mind, we now basically switch our attention to the last important component that is left, and that's a capacitor. Okay, now in the case of the capacitor, we know that the equation that relates the current to voltage is different, obviously, and that goes like this. The current now is C times the capacitance times derivative of the voltage across the capacitor with respect to time. So this time, let's assume that the voltage is a cosine omega t with a maximum voltage of Vm, peak voltage of Vm. So therefore, current becomes a C times omega Vm and minus sine of omega t. So it becomes C omega Vm cosine of omega t plus 90 degrees. So now, as you can imagine, this time the current is 90 degrees ahead of the voltage, or in other words, the voltage is 90 degrees behind the current. But in terms of the power, again, if you multiply the two by each other, P becomes C omega Vm to the power of 2 cosine of omega t cosine of omega t plus 90 degrees. So we are back into the same situation. In other words, if I draw the same plots, all I need to do is to just switch what was voltage and what was current in terms of what we drew for the case of the capacitor. Now this time what I start drawing is actually this is voltage this time, and my current, the current is 90 degrees ahead, so this would be the current. So obviously, again, the amplitudes don't have to be the same. It's a function of what the values for the capacitor and all that. So let me draw it for a more general case. So now that's the current IT. And now we multiply them by each other. Same exact thing happens. Let me do a good job right here. So becomes a maximum negative, then goes back, becomes a maximum positive, maximum negative, the maximum positive, and 0 again. So that's the power. So they look, the power exactly behaves the same way. The only difference is that now the voltage and current, we just switched the two, but at the end the result is the same. In other words, what I'm saying here is that again the average power for the capacitor is the same as what it was for inductor, in other words 0. So we can extend the discussion that we had for the capacitor. In other words, there is no power consumed in the case of a capacitor. We are not transforming any of the electrical energy into a different domain. The only difference between the capacitor and inductor is that the energy was conserved in the form of kinetic energy or magnetic field in the case of an inductor, whereas in the case of a capacitor, the energy is conserved in the form of a potential energy or charge or electric field, and then it comes back to us in the next period of the power as it becomes, just switches polarity from negative to positive, and it just keeps repeating like that. Okay, so with this discussion, we're now ready to write the equation for a general case where what is in the box is not necessarily one component and is just an impedance, and therefore the phase difference between the current and the voltage is not necessarily 0 or 90 degrees as it was the case for the resistors and capacitors and inductors, and it would be an arbitrary phase difference of theta. And we're going to write the equation for that case in the next lecture and make general conclusions out of that equation. Thank you for your attention.